All right, ladies and gentlemen, welcome to another round of AP Chemistry Information. This is Mr. Doolin. Thank you for tuning in for this. Today, what we're going to do is we're going to take a look at empirical and molecular formulas. For most, this is going to be a review from some things that you've done in pre-AP chemistry, but we'll take it to the next level as far as how we can be given information. So definitely want to be familiar with those types of things, all right? Okay, so empirical formula, what is it? It is the simplest molar ratio of a compound, all right? So it is the simplest molar ratio of a compound. Now, empirical formula is very similar to what we were doing with the law of multiple proportions, but, and this is a big but, empirical formula is a molar ratio, whereas law of multiple proportions was a mass ratio. So definitely something that you want to get compartmentalized in your mind and in your memory, because the two processes of solving things out are pretty similar. Because we're just going to be creating these ratios with information that we're given. So definitely, man, I would write that down in my notes and just get the idea down that it's similar to the law of multiple proportions, but empirical formula is a molar ratio, whereas multiple proportions is a mass ratio. So empirical formula, molar ratio. Multiple proportions, mass ratio. All right? So make sure you got that down. So how are we going to be given information, or what are we going to do? Well, the general flow of an empirical formula is we're going to have an amount of something. We'll have an amount of all the different elements that are present. We're going to convert those to moles using stoichiometry, and then we're going to make a ratio, right? And again, these should be small, whole numbers, and the reason for that is that these ratios actually become subscripts. All right, and I dare you to find any molecule where subscripts will be listed as anything but a whole number, okay? And so how will we be given information? Well, our amounts here could be percentages, they could be masses, they could actually give it to us in grams, kilograms, whatever it is. It could be moles. All right, and so one thing I definitely want you to be prepared for here with your amounts is be prepared to use definite proportions and percent compositions to determine these amounts. All right, and so what I would do is, before I moved on from this, is I would make sure that I could in my head picture how could they give me information using definite proportions to determine these amounts. And so I will say I'm going to write this down because that's how strongly I feel about it. Let's be prepared to use definite proportion to determine amounts, right? And in your head, kind of go through what that might look like, and be ready to deal with that. We'll definitely have some sample problems that I'll do with you with that, but it's better if you can kind of pre-visualize those types of problems before you actually see them. All right. And so some other things that we'll see with empirical formula that's really popular is called hydrocarbon combustion analysis. And I think it's important for you to see, and a hydrocarbon, hopefully you remember, that's really just a compound that's made up of hydrogen and carbon. Are the only two elements present. And so what we do is we do something with it called a combustion analysis, and we've got an apparatus that's actually got three vessels, if you will. All right, and I'm going to go ahead and show off my art skills here. There we go. There we are. All right, and so one of them, I've got my actual sample, whatever it is, and so here's my sample. In another one, we've got a CO2 collection area. And then in the third one, we've got water. Water collection. And we do it this way because hydrocarbon combustion Hydrocarbon combustion is always going to be some CH compound, right? And so I'm going to say CXHY, whatever it is, plus O2 for my combustion is going to give me H2O plus CO2, all right? And so water and carbon dioxide, when you combust a hydrocarbon, those are the only products. And so when we collect whatever it is here, we can actually, if you go back and think about the unique elements that are found here, I've got carbon, I've got hydrogen, so my water would be used for the amount of hydrogen, my carbon dioxide would be used for the amount of carbon that was actually present in the original sample. All right, so again, we're looking for those unique elements that can relate back to the compound that we're interested in, and this is a very common way that we do this with hydrocarbons. There is a specific type of hydrocarbon that I want to point out because it's kind of quirky in this way. An alkene, which is any carbon-hydrogen compound that's got double bonds in it, has the general formula of CnH2n, and its combustion is really unique in this fact is that the N's actually can give us molar amounts of the water and the carbon dioxide. So something that you probably want to store away. You could figure this out, but something that if you remember this trick is going to save you some time later on, and we'll look at some different types of problems that involve these alkenes, and you'll see what I mean. But the cool thing about it is that no matter how many moles or what amount I've got here, it's going to produce the same amount of water and carbon dioxide in the form of moles, right? It'll produce the same amount of moles. It does not matter the amount of the alkene I actually have. So very unique in that respect, all right? Okay, so empirical formula, looking to figure out how we can get it to that smallest whole number ratio. Remember, it's a molar ratio and not a mass ratio like our multiple proportions was. All right? Okay, so now let's clear this up, and let's take a look at molecular formula really quick. So molecular formulas, they are not the simplest whole number ratio of our compounds. For example, if I had CH4, I can't reduce those subscripts anymore, but if I had C2H8, 8. Now you see I've got a common divider in my subscripts. I can actually reduce those just like I would reduce a fraction, all right? And also the cool thing about this is you can see from an empirical formula, which this would be my empirical formula, all right? And my molecular formula over here, there's a multiplier that exists between the two, and the multiplier in this particular case is times 2, all right? The other thing that we want to take a look at here, because since they're just a strict multiplier, you're just doubling, in this particular case, the number of atoms that are actually there. The masses are also multipliers, and so something you definitely want to get down. So the formula mass of CH4 is 16 grams per mole. Well, my multiplier was times 2, so this one's going to be 32 grams per mole, right? And you can actually add those up and double check my math, but I'm telling you it's going to work out. All right? And so not only are the molecules multipliers, the masses are also multipliers. And so what do we use this for? A lot of times we can do a combustion analysis on these hydrocarbons and we'll get the empirical formula, but we know that doesn't represent the molecule that we're actually studying because we understand that the mass of that molecule is different. All right? So what we can do is we can figure out the multiplier. We can do it two ways. Number one, we can either, the most common way, let's start with that one, is we'll take the mass that we know, divide it by the mass of the empirical formula, and that gives us our multiplier, right? And then I would know, hey, I figured out the empirical formula because I can do that mathematically. My multiplier is times 2, so I would just multiply all the subscripts by 2. That would be my molecular formula, all right? And so don't get crazy with that, ladies and gentlemen, because really it's just the mass of the molecular formula divided by the mass of the empirical formula, and that equals my multiplier. And this is actually pretty much the exact same way that we did it in pre-AP chemistry, and so there's not really anything to add here with molecular formulas, but empirical formulas will get the information in a couple of different ways. The biggest jump right there is the integration of definite proportions into my empirical data that they're going to give me, where I will start and have to figure out the amounts present of everything using definite proportions, okay? So hopefully this was clear. If not, make sure you got your questions down. Let's address those in class so you can come to tutorials. And thank you for tuning in. Thank you for making it through another round of AP Chemistry Lectures with Mr. Doolin. And I will see you in class.